welcome back. We have been looking at the resolution method for first order logic, and we saw that problems that we could not solve using forward chaining and backward chaining, we could solve using the resolution method. We have not spoken about the equality predicate so far, and let us talk about that now. So, we had said that when we talk about first order logic, we can say first order logic, or we can say first order logic with equality. What do we mean by that? That this is a special predicate that we are including in our language. Not only are we just including it as another predicate, but it has certain properties which we will need to exploit if we want to make all the inferences that are entailed. So, to recall, the atomic formula that we use, that we construct using equality, is T 1 equal to T 2, and the interpretation of that is that if the image of T 1 under the interpretation and the mapping function is equal to the image of T 2, then we can say that the formula is true essentially. So, if we say, for example, that this formula is true, then this formula would be true if whatever this pointed to in the domain is also pointed to by this same thing, whatever it is. So, some element in the domain, but both the left hand side and the right hand side must point to that essentially. However, even simple things where conclusion is entailed cannot be proven without some additional knowledge, and so we will look at what is that additional knowledge and how do we use it. So, here is a very simple knowledge base. It says there is a variable n whose value is 5. So, we have written this as n equal to 5, and then we are saying that m equal to n, m is another variable, and we are saying it is equal to n essentially. Now, clearly if m is equal to n and n is equal to 5, we should be able to conclude that m is equal to 5, but how does one prove it? So, remember that when we talk about logic, we are interested in proof. We are simply interested in blindly being able to pick a matching pattern and then apply a rule and add the new pattern and so on and so forth. How do we make sure that we can add this new pattern? So, clearly with just using modus ponens and all, you can't do all that, because of the fact that there are no implications here, there are no logical connectives that you can work with. Remember that logic rules, they work with connectives. So, modus ponens works with the implication, the resolution rule works with the disjunction and so on essentially. There are no connectives here. So, how do we go around doing this? The reason we can't do it very simply is because the predicate equality is not just any other user defined predicate. Of course, you could have defined equality by saying equal T 1 T 2. I can say this is what I mean, but unless I add some more knowledge about what does this equality, what are the implication of using equality, or what does equality entail, we should not be able to prove even simple things like if m equal to n and n is equal to 5, then m must be equal to 5 essentially. So, equality is not just any other predicate, it has some very well defined semantics and some properties that need to be added to the knowledge base, and these properties are known as equality axioms. So, let us look at that, and then we will see how we can prove this particular simple fact that m must be equal to 5. So, what are the equality axioms? Basically, these are axioms which tell you what is the properties of the equality relation. So, the first property is reflexivity. It says that for all x, x must be equal to x. I mean, it sounds trivial, but we must have it in the system if we are able to prove certain things. Then symmetry for all x, for all y, if x equal to y, then it means that y is equal to x. Again it may sound obvious, but it is a property, it is called symmetry, and when we study relations, we know that some relations are symmetric, some relations are not. For example, being taller than is not a symmetric relation. If I say Suresh is taller than Ramesh, then it does not mean that Ramesh is taller than Suresh. In fact, that is not symmetric, anti-symmetric, not anti-symmetric, it is not symmetric. And transitivity. So, many properties are, many relations are transitive, but we must explicitly state that for equality, that equality is also transitive, and what it says is that if x equal to y and if y is equal to z, then x must be equal to z. Then substitution for functions. So, if we have function symbols in our language, then this axiom must be added. It says that if s is a function symbol of arity n, then it takes n arguments. So, let us say if we have x 1, x 2, x 3 up to n and y 1, y 2, y 3 up to n, and if we say that x 1 equal to y 1 and x 2 equal to y 2 and up to x n equal to y n, then it must be the case that the function f on x 1 to x n is equal to the function y on y 1 to y 1. Why do we use equal to here? Because these are terms, essentially these are not formulas. And we will see that this kind of things, they play a useful role. For the example that we are looking at, we will need that substitution for predicates. So, for every predicate of arity n, a similar property must be true, that if x 1 equal to y 1 and x 2 equal to y 2, it should be up to x n equal to y n, then the predicate on x 1 to x n must be logically equivalent to the predicate on y 1 up to y n. So, we will see a couple of examples which illustrate how these axioms can play a crucial role in proving certain things. So, since we are doing the resolution method, we will convert them into clause form, but these axioms hold irrespective of what form you express them in. So, this is the same axioms in clause form. The first one does not change, it simply says x equal to x. Of course, it is now in implicit quantifier form. So, we have thrown away the quantifier. The second one says, what did it say? It initially said that if x equal to y, then y is equal to x, which has been now converted into clause form. So, we have said either x not equal to y or y is equal to x, which is the same thing. So, remember that this is the same as saying p implies q. If the left half on the red is p and the right half is q, then you are saying p implies q, which is not p or q. This we have done the same thing here, but very often we want to, instead of using the negation sign as a logical symbol, we often use the negation sign as an infix form, because sometimes it is easier to read. Otherwise, these are just two different ways of saying the same thing. So, transitivity is similar. So, we could have said it using the negation sign here, for example, but we can also use it by using it inside, and some people feel that the right hand side is more legible than the left hand side. It's up to, it's a matter of choice, I suppose. Maybe if you add brackets, it might become more legible, but then the formula length keeps growing essentially. Likewise for the other these things. what we have done is we have used this symbol here, and this one is does not change. But when we come to predicates, because logical equivalence is it is like bi equivalence. If you look at this formula P, or let us say alpha, if you write alpha is equivalent to beta, actually this is equivalent to writing alpha implies beta and beta implies alpha. You can work that out, because you can go from left hand side to right hand side. So, this one says that you can go from alpha to beta, this one says that you can go from beta to alpha, and that is the equivalence anyway. So, when we do that, we get this, we get one of this as negation. So, we have removed the implication and replaced it by not and or, and the other one is this one here essentially. So, without loss of generality, we do not want to write the other part. So, we write this one part, and that is enough, because anyway x 1, x 2, y 1, y 2 are variables, and if we choose them carefully, we can get a proof here. If you choose which one do we mean, we will get a proof, and we will see this in a small example. Here is just another version of the same thing, and I have done this simply because sometimes this is more legible than with all those question marks hanging around. In Prolog, this is in Prolog style. In Prolog, all variable names are capitalized, and we will look at Prolog a little bit later in this course. In Prolog, all variable names are capitalized, all constants are in lower case. So, because we are talking about variables here, we can replace them with uppercase letters x, y and z, and as you can see, it is perhaps a little bit more legible than it was earlier. We will use both forms. So, first let us look at our simple problem that we could not solve without the equality axioms. What was the problem? The problem was that if you are told that n equal to 5 and if you are told that m equal to n, you must show that m equal to 5. So, when you say you must show that m equal to 5, we mean that we must produce this exact formula as a conclusion essentially. But we are doing resolution refutation. So, we will be happy to take its negation and then derive the null clause. So, here is one proof, and you will see that we are using the equality axioms here. So, there are two facts given to us, n equal to 5 and m equal to n as shown here, and we start using the equality axioms. So, this is a symmetry axiom, if you remember. Then from the symmetry axiom we can conclude that 5 equal to n. So, that is the thing about logic, it is like very bureaucratic, you might say. You must show me the exact pattern, and only then I would be happy. So, saying n is equal to 5 is equivalent to saying 5 is equal to n, but if you are doing a proof, then you must have a way of converting from n equal to 5 to 5 is equal to n, and the symmetry axiom is very convenient for doing that. So, what is happening here? We have n equal to 5 and we can match it with this not x is not equal to y. So, we will cancel that, and then of course, we have x and y, and x was matching n. So, n comes here, and y was matching 5. So, for 5 will come here. So, it is like swapping them, and the symmetry rule does that for you. Then we use the transitivity rule. If x is equal to y and y is equal to z, then x is equal to z. This is expressed in clause form. So, notice that the first two are negated. So, and the third one is not negated essentially, and we are matching this 5 equal to n with this one that has been shown in the red. So, that will get cancelled, and the remaining two will come here, and what we will get is n is not equal to z or 5 equal to z essentially. So, we want to use that. So, somehow we want to bring in m here, but our formula here has n as the first argument and the other thing as the second argument, whereas our fact says m is the first argument and n is the second argument. So, again we must use the rule of symmetry to flip that formula. From m equal to n, we got a new formula n equal to m. Now, of course, this new formula n equal to m will match this n not equal to something, and we can cancel that off, and we will be left with the formula which is 5 equal to something. And what is that something? That something must be m, because when we are matching z here, we are matching with m. So, that m must come here. This is what we wanted, or this is what we almost wanted. We wanted 5 is equal to m is equal to 5. What we have got is 5 equal to m. So, we can, by now we are familiar with this process, we use the symmetry axiom to convert that into m equal to 5 essentially. So, we have a proof for m equal to 5. So, luckily we can do this basic maths that other kids can do. And just for the sake of completeness, since we are talking about the resolution method, we take the negated goal and then we can derive the null clause, and that is where our resolution refutation method will end essentially. Now, search is something which has been implicit in everything that we have been saying. I kept saying take some two clauses and resolve them essentially. How do you resolve them? You look for a literal. So, let us call this L, and in the other clause you look for a negated literal. So, just try it as an exercise that instead of doing this flipping using symmetry, just try using it directly with the clause which talks about transitivity. And if you were to take the match this literal and treat this as not of L, you will see that it will not be such a straightforward process, which is why it helped us that first we flipped that L into using symmetry. So, instead of saying n equal to 5, we said 5 equal to n, and then it worked out for us essentially. But we have choice. We have made choices at every stage. So, we said which two clauses to pick, and even when you are resolving two clauses, which ones to pick. So, instead of treating this as not L, what if we had treated this as not L, the second clause? Would things change? They do. So, let us look at that. This is a much shorter proof. Same problem, same knowledge base, it is just that the choice of how to resolve clauses is different. So, instead of using the symmetry clause, remember in the last proof we used it 3 times. 3 times we inverted a formula of the kind x equal to y is equal to x, and that was necessary in some sense, but it sounds a little bit of excessive this thing. It turned out that because in the transitivity clause we were using the first clause, it was needed, but if we use the second literal in that clause, things work out much faster essentially. So, instead of matching with x not equal to y, if we match it with y not equal to z, then you can see that y will match with n and z will match with 5, and we will eliminate that, and what we will get is this n has come here and this 5 has come here. So, we get x not equal to n or x not equal to 5. Now, this x not equal to n is very conveniently going to match ours, which says that m equal to n. So, we can cancel that off, and what we get, voila, m equal to 5, that is what we wanted. So, in just 2 steps we have got what we wanted to show essentially, as opposed to those 3 extra axioms of symmetry that we had to use essentially. And of course, with if you are doing the resolution method, you can use the negated goal and derive the null clause. So, a small change in choice resulted in a much shorter proof, and that is a problem with automated theorem proving has to contend with, that if you can choose between many options, how do we decide which one to go for next essentially, which is why it is a problem that is worthy of attention. We mentioned a couple of strategies on the way. We said set of support strategy, unit clause strategy, but here its problem is a little bit finer than that. We have decided that we want to use n equal to 5 with the transitivity clause. The choice was whether to match it with the first literal or the second literal. The first literal involved using the symmetry clause 3 times. When you use the second literal as here, we can do it directly essentially. So, we will see that logic that theorem proving is not a inexpensive process. It requires a lot of work essentially on the part of the machine essentially. So, this example has shown us the equality axioms and how we use them. When we come back, I want to take another interesting problem and see how we can use equality axioms, because we have not used the substitution rules here. We have just used the rules of symmetry and transitivity here. We will take another example in which we also want to use the rule of substitution. We will do that in the next meeting.